Okay, I've changed my my output to the speakers. Can people still hear me?
Yes, we can hear you, and honestly, it doesn't seem any different. You're
Okay, but
fine. You're fine, loud and clear.
okay, super. Okay, so back to the slides. So before we start, I wanted to see if anyone had any questions about this week so far. Okay, great. One thing I did was I noticed that the two notebooks that we were looking at this week are really similar. So I combined the two notebooks into one, and it's right now on the course repo on our study group's repo, and it's called I think I just called it the name of this second one. Let's see, make sure that I'm sharing the right thing. So share. Find that one that shares everything. I want, yeah. Okay, so are you seeing the notebook predict, and at the top of it, it says predicting English word version of numbers using an RNN?
Not right now.
Oh, okay, then I'm sharing the wrong thing. Hold on for a sec. Share, this one. How about now?
Yep.
Seeing the notebook? Okay, so what I did was I took this notebook 6-RNN-English numbers, and there's another one called 6-RNN-English numbers underscore GRU, and I combined those in one notebook. Basically, the second notebook was just a few things added on to the first one. So now there's only one notebook 6, and it's called 6-RNN English numbers underscore GRU, and that's got both notebooks combined. Okay. But before we go into this notebook, I wanted to look at the slides that show some really nice slides from this MIT course that show us what an RNN looks like and what it does. So let me go back to sharing that, and then we'll come back to the notebook. Stop sharing that. Start sharing that. Screen standard RNN. This is the one. Share. Okay, so normal outline slides order, that's the one. Okay, so this is the RNN. This is a sort of a schematic for what an RNN looks like. It is a fully connected network that starts with an input and produces an output, but it has also this hidden state, so that when it makes the output is combined version of the input hidden state and the input data, and then it passes on the output as the next hidden state to the next, because what an RNN is a recurring neural network. Recurring means that it occurs one after the other. So we basically can visualize this set of fully connected neural networks along a line. There's a bunch of them connected like this, and each one gets the input of the hidden state from the one before it, and takes another input and produces another output. So this is it's a set of repeating fully connected neural networks. Okay, next slide. Page down. And this is a schematic for what it looks like. This HT going back in is kind of like a schematic that says, repeat this thing, T times along the line, and we'll see what that looks like. But the main thing is to look at the computations of how the output gets computed from the input. And you can see that it involves 3 matrices. One is HH, which stands for hidden state to hidden state. One is WXH, which stands for input to hidden state. And then the last one is WHY, which stands for hidden state to y, which is the output. And so this shows mathematically how everything gets computed. So the hidden state gets computed from the hidden state before it and the input in this way. So you can see that the schematic says the input goes in, the hidden state goes in, in other words, the previous hidden state goes in, and the next hidden state goes out. And this is how it's computed. So there's this, you have the hidden state from time t-1 multiplied by this matrix WHH, and then you add it to the input vector xt multiplied by the matrix WXH, which maps the input state to the hidden state. So the sum of these two is then taken through a tanh function, and the output of that is the hidden state for the next layer. That's how that works. And for the output, it's a different matrix that multiplies HT, multiplies the hidden state by WHY, and that produces the output. Okay, and so we want to keep this in mind when we go through the implementation of this thing. Okay, next slide, we put this together, and so this is what this symbol stands for. I want to make sure everybody's seeing what I think I'm showing, which is a slide that says RNN's computational graph across time. Is everybody seeing that?
Yeah.
Okay,
Yep.
Great. So so this is the compact representation that we saw on the last slide, and this is what it looks like when you unroll it. So there's a hidden vector, there's an input vector that has t elements to it. I guess it looks like t plus 1 because it starts at x0. And there's the output vector has the same number of elements in it. And in each case, the output vector and the next hidden state are computed by using these same matrices, the same three matrices. So there isn't a different matrix for every element. There's the same matrix WXH gets applied to the input here, gets applied to the input here, here, and here. The same matrix WHH gets applied in this cell, this cell, this cell, this cell. It's the same matrix WHH, and again the same matrix WHY. So there's only three different matrices of weights that have to be solved for in this. And that's one thing that I guess that's one reason why they're so fast. If you're trying to predict the next word, and that's what we're trying to do in a language model, you want to predict the next word. So the first word comes in, and then the prediction for the next word comes out. And then you compare them and you compute a loss function, depending on how good you did or whatever. So there's a loss function for each of these elements, and all of them taken together is the whole loss function L. Okay, and next.
Where's the hidden? Can you relate this to hidden state?
Yeah, the hidden state is what goes in at the left and comes out. The previous hidden state goes in at the left of each cell and comes out at the right of each cell. And the computation that produces that hidden state is what we saw on, what we saw on the previous slide. So this is the mathematical computation of that, of the H. Each hidden state, the next hidden state is computed from the previous hidden state and the current input.
So it's just a matter of doing computations on this matrix that gets passed on and then gets augmented and passed on and augmented and passed on. That's the hidden.
That's right. That's right.
Okay.
Yep. Page down.
And just here, like there are three different weight metrics here, like WXH, WHH, and WHY.
Correct.
What are three different? Are these three different weight metrics, or one is the output? I get confused. Why we have a three weight matrix?
There's three different weight matrices because we're doing operations that map input to hidden, hidden to hidden, and hidden to output. And each of these matrices has to have different dimensions. We'll see that as we go on. We'll see that the three matrices are different and they have different dimensions.
So you do, and you're doing them in order, right? Like the WXH, and then you use WHY, and then you end up with WHH.
Yeah,
you doing
and then once you have WHH for the first cell, you can then do the computation for the second cell, and so on. And so this slide shows, you know, how the forward computation flows with the black arrows, and then it shows how the backward propagation through time flows with the red arrows. So you start with the loss function, and then when you do your stochastic gradient descent, you're tracking through the derivatives in the direction of the red arrows. And so the whole thing has to flow back, ultimately back to the first cell. So that's why this red arrow flows from, the overall red arrow flows from xt all the way back to x0. So remember, in a neural network, there's always a forward pass and a backward pass. The backward pass is when you're computing the updates for the stochastic gradient descent. Okay. Oh, I have these slides reversed. Hold on. Yeah, hold on.
So you mean it actually does the whole train of, let's say you have 20 words you're putting in, it actually does the whole train to set the first prediction from the first word to the second word. It actually goes through every single word, and then it starts at the second one and does the whole.
Well, it goes through every word every token in the batch. So yeah, in other words, each batch in the way that this lesson is set up, they use 70 tokens for each line of each batch. So for each line, it's going to have 70 tokens, and you're going to have this diagram. The x0 is going to be, and then it's going to go xt, which is going to be 69. You know, and as you say, you have to compute for all 69 tokens in order to get back to the in order to update for 0 for the first token. Sorry, for the first input. But it'll be 7. The length of this thing will be 70. The way that they've done it in this lesson. Although you can control that. You know, there's a parameter that controls that called back. It's called BPTT, back propagation through time, and that controls the length of each line in the batch. So in one part of the lesson they have it set at 70, and another part of the lesson they have it set at 3. So you can control that. Okay. So this is the RNN, and the problem with the RNN is it has to do with all of these computations that have to be done, all of these matrix multiplications that are needed to produce the updates. And what happens is that you get you get this problem of vanishing or exploding gradients. That is, the gradient can get small, can start to get small, and then multiplying it, and then keep propagating it all the way back. If it's small here and it starts to get smaller, then eventually it can go to 0, and then you're not getting any information out of your updates. And similarly, if the gradient starts to grow, then this sequence of multiplications will make it grow even more, and that's called an exploding gradient. So typically so the RNN was invented, and then they found quickly that it doesn't work well with long sequences. So there are modifications to the RNN that we'll learn about later called GRUs and LSTMs that take care of that problem of vanishing and exploding gradients. But for now, we should just be aware that a standard vanilla RNN does have the problem of vanishing and exploding gradients. And so here's they say one technique that you can use to mitigate the exploding gradient problem is gradient clipping. That is, if a gradient gets bigger than a certain number, you just cut it back to that number, whatever number you had in mind, so that it won't explode. Maybe the number could be 1 or something. And then the other problem is the vanishing gradients. If there are lots of values that are less than 1, then when you propagate this backwards towards H0, you can get the gradient going to 0, and then you don't have a good your model stops training because the gradients, which is what controls the updates, are 0. So the techniques to mitigate the vanishing gradients are using different activation functions, and then of course the one they use is the ReLU, which has a gradient of, well, the derivative of a ReLU is always 1, so it never gets that big. And then there's techniques of weight initialization and network architecture, which I'm not sure what those are right now, but those are the techniques that they use to mitigate the vanishing gradients problem. Anyway, but I wanted you to have in mind this schematic of what an RNN looks like. I know Jeremy has his own schematic with the triangles and the circles and the squares, the way he thinks of RNNs. But this is the way you find it in most of the literature. They think of the RNNs this way, and to tell you the truth, I feel more comfortable thinking of RNNs this way as well. Okay, so now having that picture in mind, let's go back to the notebook and let's work our way through it. Now I got to share the notebook. Let's see. Share that. Okay, now you should be seeing the notebook, 6 RNN English numbers, right?
Yeah.
Are you seeing right? Yes? Great, thank you. Okay, so Jeremy has concocted this data set to help us, just as a simple application of RNNs, to see how we can, we're going to build our own RNNs and see how they perform on this data set. And the data set is just a sequential counting of numbers, but in English words. So the data set is basically the numbers 0 to 9,999, all in words. And he's got this data set. I'll just run through it. This is a really fast notebook. It never takes more than like a minute or so for each training step even. So it's pretty quick to go through. So we're going to read the data. We're going to, the training set turns out to be the numbers from 1 to 8,000. And the validation set turns out to be the numbers from 8,001 to 9,999. So the first thing that you can do is make a data bunch. And it looks like the default, we've already set the batch size. Somewhere over here, we set the batch size to be 64 right there, right? So it knows what the batch size is. But there's a default in there that we don't see somewhere in the FastAI code that says that the length of each line in the batch is by default set to be 70 tokens. And that's the BPTT parameter. It seems to have a default value of 70. So, so here's our data bunch, and we can look at the first few words in it. When it's XXBOS, remember, is the token for beginning of string, and the whole data set is just one long string. So you're going to have a beginning of string token, and then 1, 2, 3, 4, 5, 6, 7. Those are the first few elements, and then we can look at how the length of the thing, 13,000 for the validation set. We could also look at the training set. So above or below, whatever. And we expect the training set to be much longer, because remember, the training set is for the first 0 to 8,000, and the validation set is 8,000 to 9,999. So data.bptt, that's that parameter that we talked about, the backpropagation through time. And what that says is that's just the default parameter, 70. And the length of the data loader tells us how many batches we have in the validation set. And we can do the same thing for the training set. Set below. Find out how many batches we have in the training set. Probably the same. Oh, we have 12 batches in the training set. Okay. So here they have 13. We already saw that the where is that 13? There it is. The length of the data is the length of the validation data is 13,017 tokens. And if we divide that, remember we said that that's divided up into batches, and each batch has the batch size, each batch has 64 lines of 70 tokens each. So if we divide the total number of tokens by the number of tokens in a batch, which is 70 times batch size, 70 times 64, that should be roughly the number of batches we have, and that's that. We could also do the same thing with the training data. This is just to help us understand the data. We can do this 50,000. The length of the training set is 50,079 tokens. So we can do 50,079 tokens divided by 70, which is BPTT, times the batch size. And we expect that, we saw that we had 12 batches. If we do that division, we should get a number close to 12. And indeed, we do get a number that's close to 12. So that's just helping us to make sense of our data. So let's see. So he builds this batch iterator that pulls a batch from the data loader. So whenever you do next of IT is the iterator. So next of IT pulls out a batch. And so he just pulled out 3 batches, X1, Y1, and X2, Y2, and X3, Y3. So let's look at them. X1 plus X2 plus X3. The length of all the batches is 13,440 tokens, which is sort of makes sense because the whole thing is 13,017. Well, wait, are we looking at training data or, yeah, this is validation. So all of the validation data should be in 3 batches, these 3 batches. So this process here should basically exhaust the training data, the validation data, and pull it all into batches, the 3 batches that we have. And if you look at the length of all of them, it comes out to 13,440 tokens, which is close to the 13,017 tokens that we expected. So there must be some padding in there somewhere. Or no, maybe not padding, maybe that's all the commas and beginning of string and end of string, so on, tokens.
No, it is padding, Joseph. It's padding to make all the sentences of the same length. Otherwise, you get into problems when you.
Okay, let's check. Let's check. Thanks, Srinivas. Let's check that. X1.numel. Let's just see if they're all the same. That's 4480. Let's just see how long each one of them is. Numel is this method that just gets how many elements are in it, so counts them up. So yeah, so as Srinivas said, all of the batches are padded to make them the same length. Okay, and then as we said before, each batch has the batch size is 64, so there are 64 lines and each in a batch, and each line has 70 tokens in it. And so we can see that by looking at the shapes. And they're all the same. Okay, and the other interesting thing is to look at is the vocabulary. For this counting problem, the vocabulary doesn't need to be very large. So it turns out these are all the tokens you need. These padding tokens, beginning of string, end of string. I guess this is capitalizing. I'm not sure we even need that. I forget what XXFLD is. I forget what up rep and W rep is right now. But the only ones that we really need to use, as you can see, are the commas to separate the numbers. And then you have the hundreds, the thousands. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And then you have 20, 30, 40, 50, 60, 70, 80, 90. That's all you need to represent all the numbers from 1 to 9,999. I am not sure what this token is, XX fake, but it's in there too. Anyway, there's a total of only 40 tokens in our vocabulary, if you look at it. And so now we can start to look at what the batches look like. The first batch would be X10, and this should have 70 elements in it. Let's make sure. I think if you count all of these, there will be 70, because we know that each batch has 70 tokens in it. And notice that these are converted to their numerical equivalents. And if you want to see what, and then also notice that the Y is the next element of every one in X. So so 19 is followed by 11. So 2 is followed by 19. So the next element is 19. That's what's the first element in Y. The second element in Y should be the element that follows 19, which is 11. And there it is. So basically, the second batch is the first batch shifted over to the left. Every element in the second batch corresponds to is the next element corresponding to that same element in the first batch. So 19 is followed by 11, 11 is followed by 12, 12 is followed by 9, which is a comma, it turns out, and so on. And so this is the first, so remember, this is for a language model. The labels are basically the shifted, the same sequence, but shifted one to the left. So that's what this Y is the labels. But the interesting, or the cool thing about language modeling is that you don't need labeled data, because you just basically use the same data that you have. A shifted version of that data is your labels. Does that make sense? Remember that in our standard language, X is the data and Y is the labels. That's the way we've been doing this all along. So it's interesting to look at what the first few tokens in that batch are when you translate them back to their string versions. So let's look at this string here: 19, 11, 12. Let's see, 9, 19, 11, 13, and 9. So I'm looking at this first piece of the the first few tokens in the first batch. And if we translate them to their string values, we can see they're 8001, comma, 8002, comma, and so on. So that makes sense. I have to mute everybody because somebody didn't mute it. Let's see. Mute. Yeah, now everybody's muted. Good. All right. And then there's this function that's provided in FastAI, which is called Textify, and we can do the same thing. We can take the first batch and just see and convert it to its text version, and you can see it's counting from 8001 through 8017 and so on. Okay. And notice that the Y, the labels, are the same as the input, except they're shifted one token to the left, so that beginning of string in the input is followed by 8 in the label, because its next element is next. If you want to predict the next token, that would be 8, because there it is, 8. The next token after 8 is 1000, and so that appears as the second label, and so on. Does everybody see that? Okay, so we're just sort of looking at our data to make sure that it makes sense. That's all we're doing here. And then if you use this method, show batch, you can see what the thing looks like. It's sort of, we've already been looking in more detail at these at everything in our data set. So this just shows us, this is just the show batch. It shows us what a batch looks like. And remember that a batch is going to be 64 lines, and each line is going to have 70 tokens in it. So that's what we're seeing here. Okay, so now we come to the first network model that we're going to use. We're going to try to use a single fully connected model to predict the next word. We're not using an RNN yet. So, so here he makes a batch size of 64 lines, but he sets BPTT to be three tokens per line instead of the 70 that we had by default. So basically he's reforming the data bunch. We have to do that. Then we can predict the length of the data loader, which tells us the number of batches that it has for training set and validation set. And it's 261 batches for training and 68 for validation. Batch size we already had is 64. And now that the shapes are 64.3 instead of 64.70 like we had before. The number of tokens in the vocabulary, we know that's 40. We're just setting that to be an NV, number of vocabulary tokens. We're building a network, so we have to specify the size of the hidden layer, and they specified it as 64. I'm not sure why they use 64, but that's a choice they made. Let's see. We're using the cross entropy loss. We're using the normal accuracy function. So that's what we have to define, those loss and accuracy in order to use it, in order to build the network. And then this one tells us X is a batch. Let's see, did we get, yeah. We got X. Let's just make sure X dot Y equals, yeah. So X is one, so you pull out a batch here. And what does this give you? This gives you the first token in each line of the batch. Because remember, the batch is going to be 64. It's going to be 64 by 3, right? So this gives me the first. It gives me the first token in each line of the batch. If I were to ask for X of 3, what do you think I would get? Well, I get an error because there's no third element. Each line contains 3 tokens, and so there's no fourth token, so we get an error. Okay, so now here's the conventions that they use when they build this network. IH is input to hidden. Input meaning the data, this thing. HH is hidden to hidden. H0 is hidden to output. BN is for batch norm. So now we're going to build this neural network, a class for a neural network, and the first one is just going to be the simple network model 0. It inherits from nn.module, so we can use the methods from the module. We initialize it. Super.init says initialize it. Initialize the module class, and then IH is going to be the embedding of an embedding matrix of size NV by NH. Remember, NV is 40, the number of tokens in each batch, and NH is 64, the number of hidden, the size of the hidden layer. So self IH is going to be a matrix. And if you multiply, you can think about this matrix as a 40 by 64 matrix. And if you multiply it by an input vector, which is going to be, let's see. The input vector is going to have 40, is going to be of size 40. Let's see. Well, if you one-hot encode it, it's going to be of size 40, right? Because there are 40, let's see, for each let's see, each word is represented by a one-hot encoded vector of length 40. Right, and that would be, basically it tells you which one of those 40 vocabulary words you're using. So think of multiplying a vector of length 40 times a matrix of length 40, 40 by 64. I know there's a way to draw here. Let me see if I can do that. Annotate, let's see, can I do that? Yeah, so let's see. Are you seeing that? I'm drawing something here.
Yes.
Okay. So imagine a vector of length 40. I guess that should be, well, the way we will represent it, it would be 140. And then we're going to multiply it by a matrix of dimension 40 by 64. Right? Can I erase? Let's see, can I erase? Eraser, okay. I don't like this thing, so I'm going to draw that again. Back to my pen. Nope, that's still the eraser. No, I don't got my pen. Hold on for a sec. Having trouble getting back my pen here. Undo. I guess I didn't. I guess I'll just undo the erasing so that I won't lose my eraser. So what I'm trying to, oh, I did. I still lost my eraser. Let's see if I can get it back. Nope. I'm so sorry to waste your time. Let's see.
It's totally fine.
Let's see. Well, anyway, what I'm trying to draw here, which I can't draw anymore because I've lost my pen, but you can see I've got a vector of length 40 multiplying a matrix of dimension 40 by 64. That's this self IH. So this is the input vector for one word, and it's multiplied by 40 by 64. And what am I going to get when I do that? When I multiply a vector of length 40 times a matrix of dimension 40 by 64, what's the result going to be? What's the result going to look like?
1 by 64.
Okay, the matrix that I'm multiplying by is 40 by 64, but the vector that the input vector is of length 40. So imagine this long one-dimensional vector multiplied by this two-dimensional matrix, and what comes out?
1 by 64.
Yes, I'm sorry. I thought you said 40 by 64. I'm sorry. You're right. So yeah, the answer is a 1 by 64. That's, so it basically maps the word, the input word into a the input token. It maps the input token into this embedding space of size 64. That's the hidden layer. So it maps the input into a hidden layer. That's what this thing does. And then when you take that 1 by 64 and multiply it by a 64 by 64, that's this next one, H to H, you can see that that's going to map it to it's going to just map it to a 64, another 1 by 64 vector. So that's when you're mapping the hidden state to the next hidden state. You want it to have the same dimension, 64, because that's what you specified as the hidden state. Okay, and then finally, when you map to the output, you're mapping a hidden vector to the output. the hidden vector has length 64, and the output is back to using our vocabulary of 40 symbols. So you're multiplying a 64 by 40 multiplied by a 64, a vector of length 64, and then the result is going to be 40, right? Which is going to map us back to our vocabulary space. So I'm just running through what all these matrices do, because you can remember back to the calculation that we were doing that I showed you on those slides. You're going to use each of those three matrices in a calculation. Each matrix multiplies something to give you something else. The WIH multiplies the input vector to give you a hidden vector. The WHH multiplies a hidden vector to give you another hidden vector. And the WOH multiplies, or I think we called it YH, multiplies a hidden vector to get you back to a token from our vocabulary of 40 tokens. So are there any questions on that? Just going through what all of these things do.
Not right now.
Okay, so the first one is kind of, the first module, it basically is a sort of a brute force thing. He knows that there are 3 batches, so he processes them one by one. So, you know, the first one, the second one, the third one, and then he returns the output. But I think it's instructive just to go straight to the to module 1, where he does this the right way. He refactors it to use a loop. Now I'm going to try to get back my cursor. Let's see. Clear all drawings. Clear all drawings. There we go. Still can't get back. Clear all drawings. Undo, 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 undo. I'm stuck with this eraser that I don't want. Can't get. Hold on for a second. I'm going to stop sharing for a minute to see if this will go away. And then I'll start again. Share it back. And there it is. Okay, I got rid of that thing. Okay, so this is module 0, which is, remember, it's a fully connected network, and it's trying to predict the output state. It returns the output. So, you know, he builds the learner based on model 0 and the loss functions that we defined. He trains it for 6 cycles, and you get up to 46%, 47% accuracy after 6 cycles, which isn't that great. Now he just refactors this thing. We should have looked at this. This should have been the starting point, really, because you don't do things in a brute force way like this. You want to make this general so that if you have 10 batches or 11 batches or 2 batches, it works the same way. And that's what he does too. He loops through the batch size x dot shape of 1. Sorry, the loops through the number of batches. Remember, x dot shape of 1 is the number of batches. Let's go back up here. Here's the x shapes. 64. Sorry, not the number of batches. The number of characters in each batch. Sorry, the number of tokens in each batch. So x dot shape is 64.3, and x dot shape of 1 is 3. It's the length of a line, the number of tokens in a line. So we're going to do this for each token, predict the next one. So we have to loop through the number of tokens in the line, and that's what we're doing here for I in range of x dot shape 1. So we're computing the hidden state from the input. Then we're computing the next output state, and then we're the next hidden state, and then we're computing the output state by applying. And remember, we're applying these. Self.h0, remember, is a matrix, and self.h0 of H is a matrix operating on a vector, like we talked about before. Self.I underscore H is the matrix. Remember, it's the matrix WXH that we talked about. And self.I H parentheses XI means we're multiplying this vector times the matrix. Okay. So basically this is the, let's see, X to I. So when let's just look at this for a second more. For I equals 0, that would be the first, token in the line, And what this is X of colon I means if I is equal to 0, that means let's look at the first token in each line. And then what we're trying to do out of this, we're trying to predict the second token in each line. So that's what the output is. Okay. And so the same thing, we build the learner, we fit one cycle 6, and we get the same thing, because this is really the same. Model 1 is really the same as model 0, except it's refactored to do it the way any decent programmer would do it off the bat. So you get the same accuracy because it's the same model. Okay, now the next one is refactoring this thing to predict not just the next token, but an arbitrary number of next words. So, you know, we want to predict maybe we want to predict the 6 next words or whatever. So this is refactored to do that. And now notice he's changed the data. Now he's making the line, each line has a length of 20 now, because he said BPTT equals 20. So he made a new data bunch. There's going to be a different number of batches and so on, which we could figure out. We could get if we wanted to figure out the number of batches. But the main thing is that each batch has now a different shape. Each batch has 64 lines of 20 tokens each. Okay, so now we can do things like try to predict the next token, the next 10 tokens or something like that. And so he's refactored the model to do that. Model 2 does that now. We won't have time to go through the details of how he did that, but I think if you look at this, stare at this closely, you'll see that it's a modification of model 1 that allows you to predict more than one next token. Okay, so then we do that. We can train for 10 times, and we see that, well, our accuracy isn't as good as it was before, as with as when we're only trying to predict the next token. And here it's because we have, like, if you're trying to predict the first, he's using 70, but we only have 20 really to work with. When you try to predict let's see, we have less history to help than when we were only predicting one word. So when you predict, let's see, why is this? I got to think more about this to understand why. But it is
Joseph,
less.
in the very first model that he had is, let's stick with one number because there are multiple things which confuse the issue. Let's assume that instead of 3 words, he's just using 70 BPTT in all of the examples, just for explanation's sake. So in the very first model that you showed, what he's doing is he's only predicting the 71st word from all 70 previous words.
Yeah.
Therefore, it has 70, or let's use tokens to be consistent. He's predicting the 71st token by using all 70 tokens that preceded it.
Yes.
Therefore, he has a lot more data to predict the 71st token because he has 70 tokens that he's analyzing. Now, when you switch to this model, he's predicting every token from the previous tokens, from the previous set of tokens. So he's predicting the second token from the first, the third from the first and the second, the fourth from the first, second, third, and so on. So as you predict each of the tokens, you have less data to predict in the beginning. So obviously the overall accuracy will be less because you're not just predicting 71st from the 70th, you're predicting every following token from the previous tokens.
That makes sense. Yeah. So like if you're like going back to what you said, if we're assuming that every line has 70 tokens, when you try to predict the second line, you only have the second token, you only have one piece of data to predict from. You only have the first token. When you try to predict the 10th token, you have tokens, 1 through 9 to work with. And then as you get to the end, the 70th token, now you have all the 69 before it. So instead of having 69 tokens for each prediction now, as you did in the first model, you have 69 tokens only for the last prediction, but fewer for the predictions before that, right?
Exactly.
That's what you're saying, right?
That's why he's saying what he's saying here.
Yeah.
So, but the change in the number of BPTT and all that confuses the whole thing.
Yeah, it does confuse things because he's gone from 3 to,
right.
I think he went from 3, he used 3 in the first model because if he's only trying to predict the next token, you don't really need, he could have used 2 in fact.
That's essentially that's what he is trying to say by, and he's incrementally increasing the complexity and approaching essentially what we will be doing when we use a full-fledged RNN. So he's just trying to show that and how you can build it up from the ground up. So
yeah, and the other thing that we notice is that when you have only 3 tokens per batch, you have a lot of batches. You have a lot of batches to work with. So that's another reason why the first model would be expected to have better accuracy, because you have way more batches to work with in your training set. But anyway, the result is we got a poorer accuracy. So the next thing is you now try to implement this RNN where you have the let's see, sorry, let me go back to the first one. I want to look at it for a sec. It has IH, HH, and HO. This thing also has IH, HH, and HO, but there is extra operations in here. So if we were to compare this with model 1, see, this is the one where we've already done this one. This is the one where we got the poor accuracy. So this is model 3. This is the one that we want to compare with model 1 to see what the difference is. And so all of this is the same. But now he's got this new thing which he calls result, or RES. So let's see what he does here. This looks similar. This looks similar. rs.append self.batch.
So here the bottom line is you just store the hidden state. So you don't start with 0 for every line of text. You start with what you had stored in H previously by processing this line of text. So that's essentially the difference between that.
Right. So now we're using that hidden state.
You're storing it, so you reuse it. You store it and then reuse it as you move to the next line of tokens, rather than starting fresh for every new line.
Right. And then self.h is h.detach. I'm not sure what that, detach means that you don't want to keep track of its gradient, right?
Yes.
Okay. Let's see, self.h result equals torch.stack. Result 10 equals 1. So this is result equals self.h0 result. So this is the output, and it's
so intuitively it's the following, that for every line you compute the h and you want to continue to propagate, you want to continue to do the BPTT, which is back propagate through time, for 70 tokens. Now, when you get to the next line, you want to carry forward the hidden state, but you don't want to carry forward all of the differentiation of the hidden state with respect to the first line. So you detach it, which means you say that I don't want to continue to carry all your derivatives. I just want to take the value and shove it into the next iteration and then compute the new derivative with respect to the new set of tokens. That's why you do the detach, but then you append and carry the h forward to the next line. Does that make sense?
Sort of, but now self.h is h detached. Where does h get used here?
Oh, in the next, the taught that stack results, because in the result you have appended the batch normed h. So you in the result is a list, and the result which is what RES stands for, and there you are appending the h for every line as you go through the lines.
Yes. So result is the actually h with a batch norm
Applied to it.
Applied to it. Yeah.
Yeah, that's what it is. So then the reason you do the h dot detach after you have appended it is because you want to carry forward the h, but you don't want to carry forward the h and its derivatives with respect to the first line of tokens. You just want the value, and you've detached all of the derivatives from the first line. Now you take that value and you start differentiating and you start multiplying as you go forward, and it automatically does the backward propagation, but with respect to the second line or the second set of tokens.
Okay, I'll have to think about that one.
So after, at the end of each line, you compute the hidden state. You want to carry forward that hidden state, but you don't want to carry forward the hidden state with all of its derivatives with respect to the first line. You don't want all the derivatives to go as well, and that's why you detach and you say, just give me the values. Not if you just took h as is, the way PyTorch and any other framework works is it continues to differentiate not just with respect to whatever new computation, it continues to differentiate with all of the computations that have occurred so far. So it means it will continue to differentiate with respect to not just this set of tokens, but the previous line of tokens as well, which you don't want.
I see, because because you're doing this line by line. You're
Exactly.
Okay.
That's why you detach at that point.
Forward is forward going through your line, right, of tokens,
Correct.
right?
That's
Step
more
by
the
step.
matrix.
And you're returning yourself is what you're doing. The response is you're returning this object, this instantiated class, but with updated H. The H attribute.
Yes, eventually you're returning actually the, from the forward, you're returning the output, which is the self.ho, which is that matrix, the H underscore O matrix multiplied by res.
And so it's going to predict, the output state is going to predict all the next, all BPTT of the next tokens.
That's right. Yep, right. Every one of those, yes.
Yeah. Okay, so then he trains this thing, and let's see, learning rate 3 times 10 minus 3. I just want to see if this is the same learning rate. He's fiddling around with the learning rate, and I'm not sure what this % start is either on this process. Learn.fit 1 cycle, 10 epochs, learning rate of 10 to the minus 4, and I'm not sure what this is. We could actually find out if we wanted to by just we could go I think we could do something like that to figure out what the line, slice. I'm looking for the PCT start. I'm not sure what it's. So it's defaulted to 0.3, and so they've set it to 0.1 in this here, but I'm not sure what it actually does. We'd have to look at the code to figure out what it does. Okay, not worth looking at right now. So let's just move on. Here, so the next learner, he just leaves it at 0.3 for the RNN. Fit one cycle for 20 cycles, and you see that it rapidly, well, let's see, after 9 epochs, it was 36% accuracy. And here, after 9 epochs, it's already up to 53%. So really has given an improvement. And it seems to get stuck at 53. It doesn't really get any better after you go up to 20 epochs. But the point is that you're getting a lot better. 53 is a lot better than 39%. Okay, now he says, all right, we built our own RNN here. Now let's use PyTorch's internal RNN. And so here's the code for that, model 4. And somehow it does a lot better. so we had 53% accuracy. Now all of a sudden with PyTorches you get 70%. And so one question is, why does PyTorches do so much better? I don't have the answer to that question, but that's interesting. And then there's this thing called a GRU, which is the same as, it's basically the RNN architecture with an extra gate. And I haven't shown that. I suspect we're going to look at that more in a later lesson. But right now, the reason for the GRU is to get over the problem of the vanishing and exploding gradients. It seems to solve that problem. The GRU architecture and the LSTM architecture also, which are variants of the RNN, but they're variants that have been found to reduce the problems with the exploding and vanishing gradient, with the result that you get a longer memory. You can remember a longer sequence of tokens than with just the plain old RNN. So we build this. This is the architecture of it. We should actually study this, but we don't have time to in this lesson to see what's different. And then we see that, okay, remember we had 70% at the end of our RNN. With the GRU architecture, we get 79%, which is a huge increase. And notice that even on the first epoch, this thing already has 46%, which was better than our own version of the RNN did. Okay, so now we used PyTorch's internal implementation of the GRU. So now Jeremy builds the same architecture, but from scratch, or at least more from scratch than before. Gets the same accuracy, 79%. So model 6 is equivalent to model 5. And it gets roughly the same accuracy. And then the third iteration, he builds a custom GRU cell. I'm not sure what, oh, here it is. GRU cell, super GRU cell. I don't understand this structure here, because this is the class that inherits from N and module, and then he's doing super GRU cell self. I'm not sure what this line does.
That's
anyway,
the Python 2 version of super init. Joseph, it's just the fact that in Python 2 you needed to supply the enclosing class. Typically, if you see in Python 3, it will just be super open, the brackets, then the init brackets, which is initializing the module. You just shown it in the earlier case. This is just the Python 2 syntax version of the same instruction.
Oh, okay, because I thought super means that initialize the class that this is inheriting from.
Yeah, and it's the same thing. It's just in Python 2, you had to supply it. You had to supply the GRU cell and then self, whereas now with Python 3, you can just do super brackets, under init brackets.
Oh, okay. So you're saying that this could have been written.
It's just replace it with super open brackets, just like you had in the yeah, exactly.
Like that?
Right, exactly. And it wouldn't make a difference if you're running Python 3.
I see. Well, thank you for that. So that would make more sense to me if I would have seen that. But anyway, okay.
That's a Python
So,
2 to 3
I see.
syntax
And we're all
change.
using Python 3 now. So
Right. So that's from Python 2 layover.
okay. So I suspect we're going to want to get into the details of what GRUs, of how GRUs are constructed, and maybe I think that might happen in the next couple of lectures. But for now, we'll just take it on faith that this GRU cell works to improve the memory, sort of. In other words, a plain vanilla RNN can't remember very long sequences, but with the GRU architecture or the LSTM architecture, which we'll learn in the next few lectures, it has a longer effective memory. Okay, so now what's modules? So this is our GRU cell, and then module 7 uses it, and it seems to have not quite as good an accuracy, but the thing is, when you run these things many times, you can get pretty variable results. So I'm not prepared to say that 75% is a lot worse than 79%. I think if you run it again, it might come up to 79%. But anyway, so that's the end of this thing. We've seen how to use RNNs to memorize sequences, and then we've seen the variants of RNNs that help to make the memory longer. The GRU, that's the variant on the RNN architecture that helps to make the effective memory longer. Probably it would be interesting to see what you could predict. I'm thinking of how we could use our model to generate the next, give it an input and then tell it, and then generate the next line. I don't see how to do this from here, but let's see. So it's predict. Learn has a predict, I think. Let's see. Insert cell below. Learn. I want to see the methods of learn. So I think there's a predict method or something. Learn. Create.
Is this a fast AI object?
Yeah.
Or PyTorch? Okay.
Yeah. So I want to see how we can use our result to predict the next line. So here is learn.predict. I should be able to do something like
You mean predict tokens, not lines?
Yeah, predict. I want to give it some tokens and then predict the next one. So I should be able to give it a part of a batch. Let's say x of 0. Let's see. I forgot what x looks like. X is a let's see. X is 60. X is a batch, and it's 64 by 70. So what if I took x of 0, 10? Oh, and it's 20. I think it's 64 by 20. So if I did x of 0, and then let's say 5 through 15. Let's see what it does. Oh, it doesn't like that. I'm not using the syntax correctly. I'm thinking that I should be able to give it some text and have it predict the next line. So I want to give it something like 1,181, and then I want it to predict the next letters, the next numbers. I want to see that it does that. So there's a way we should be able to check that. We should be able to give it some input and have it predict the next. Why does it not like this. It says only one element tensors can be converted to Python scalars. Hmm. Or by 20. So it's a tensor. One element tensor. Well, anyway, it'd be interesting to play with this because there's a way to do this. There's a way to make it show what the prediction of the next line is. And if I have more time, I'll fiddle around with this and see if I can.
I have a question about this. So I have some rough intuitive understanding of what the RNN is doing. You know, with the hidden state, and you end up with basically the same vector space matrix dimensions and shape that you put in, you get out, and you're putting in the embedding space, right?
Yep.
And that's the way. So what I'm trying to understand intuitively is the prediction of the next word. Is it because you take that output and your prediction layer then queries that in the embedding space to find the closest word in that embedding space? Is that how what you're trying to do now? Is that how the actual prediction works of the next word?
Let's see. Well, we already know the next word, so it's trying to train the network
right.
so that it.
Yeah, go ahead.
Yeah, so we already know. Remember, we already know the next word because it's, you know, we have a string of text. Every word has a next word. So we already know the answer. And so we're trying to train the network trying to train those weights so that it does the best job in predicting the next word from all of our training data.
Right, but how's it actually doing the predicting? I mean, even during the training, how's it doing the predicting and then back propagating? It's got to be hitting that embedding layer with whatever the state of I mean, like, I just don't intuitively understand how you're predicting the next word. I mean, to me, the only thing I can understand is you've got this matrix that you're building up, and then you convert it back into the embedding space. The prediction must be query the embedding space for the closest word. If it's not that, I don't know what the heck it is. That's why it's interesting.
Well, remember, we have these 3 matrices, and each matrix has a number of weights that we're solving for in the process, in the you know, the stochastic descent process. And those matrices are the matrices that ultimately produce the output. And so we are basically twiddling around with all the weights in the matrices until we get the outputs to be what they should be.
Yeah, but you're just training to an embedding space is all you're doing.
Yeah,
you know what I mean?
Like, it's a complicated function going through multiple layers, as Joseph is explaining. It goes through just the embedding initially, and then through the modification of the hidden layer to hidden layer matrix, and then the hidden layer back to the embedding. So,
well, no, I completely understand. Yeah, I understand that, and that's interesting and great. But what I'm trying to understand is once you've done the training and you do the prediction, exactly how a prediction is done.
Yeah, but at this stage, I haven't seen anything that's able to explain anything specific more than it's a complicated function of the matrices that map it from one space to the other.
Well, no, but that explains the training. It doesn't explain the last layer, which we haven't seen or talked about, which is the actual prediction layer.
Well,
is that even
output?
We've actually talked about it because remember that's the WYH. It maps the hidden representation of the token back into the token vocabulary space.
But then you have to get a word out of that. And
That's
so
right.
that word must be coming from that embedding. So you must actually query on that output. So there is one extra step, which is you have this embedding matrix, which is the prediction for the next word, and you must query the embedding space to get that word out.
That's as Joseph said, just hidden to output. That puts you back in the embedding space if you go back and look at what it does.
Right, but then you have to have something that says, okay, you don't actually get a word from an embedding space. You get a bunch of words with how close they are in that space. And so there must be a parameter in there, you know, where it's got to choose a word, right?
Yeah, no, I'm sorry, but I think it gets you back to, because it's hidden to output. You have to go back to the H to O, and see whether it actually picks a word from the embedding, because it's just a matter of pointing to a particular entry in the embedded matrix.
Yeah, well, you can't really point to an entry. You have to. It's a cosine or something. You know, it's a vector space closeness, and it must be taking the closest word.
It picks the word, I think, because if you go back to the H to Y matrix multiplication line from the RNN code, you would see that.
No, I think I understand what Darren is trying to say, because you have, so when you do the loss function, you have to say, you know, either it predicts, in one way of thinking, either it predicts the right next word or not. And you can either say, okay, you get full credit if you predicted the right next word, but you get 0 credit if you didn't predict the next word. But maybe it's doing something more sophisticated than that. Like Darren is saying, maybe it's giving you some credit if your word is close in the embedding space. You know, if you predict a word from your embedding vector that's in some sense close to the word that you were trying to predict, maybe you get some credit, partial credit in the loss function. I'm not sure how that actually works.
Yeah, it's true. Something like that's got to be happening.
Yeah.
But anyway, it's interesting because basically you could take the prediction, the matrix that comes out, and you could use it in the embedding space in some interesting ways, right? You could take the closest, or the closest that's an entity, or the closest if you mark them that way, or the 3 closest, and observe which one really makes sense, or I don't know.
Yeah. So you're talking about the embedded, the H dimensional, the 64-dimensional embedding of the word in that space, and you can play around with those vectors before you map them and see, you know, and then they eventually get mapped back into words, back into the vocabulary space at the output step. Yeah. Let's see. Any questions about this material at all? Other questions?
The one other comment I'd make is that what's important or what's kind of a drawback of the RNN that will become obvious as we go to the attention-based mechanisms is this is sequential. So for example, to get the 71st word, you go through 70 steps. To get the 69th, you go through 68, so on and so forth. So there is a sequentialization because each HO has to come from the previous H in, and whether it's LSTM or GRU or RNN, it's all the same. There's a sequence involved. And that sequential processing is eliminated by the mechanism of attention, which makes it much faster to compute. So that's another key takeaway of RNNs. While they are great and they give very good results, they also are sequential.
So you're saying, so I haven't learned about the attention mechanism yet, but you're saying that the attention mechanism somehow keeps in mind all of the words in the entire document or in the entire line.
In the line.
Yeah, in the line. And it somehow decides how much weight to give to each word.
Yep, that's what you'll see. I mean, and if you keep that mindset of exactly what you said while we go through attention, it will help put it in perspective with respect to why they are so much faster and they have been adopted universally compared to RNNs and LSTMs in modern day processing, because they have that parallel nature versus the sequential nature of RNN, LSTMs, and GRUs.
Oh yeah. So I think that LSTMs, like when Jeremy was first making the course a couple of years ago, LSTMs was the big breakthrough. You know, the Wikitext model and all that he and Stephen Merity did, and also the other fellow who was doing his Sebastian. Anyway. Yeah, Sebastian Ruder. But then in 2017, I think that's when, well, I think 2016 was when the first attention papers were published, but they didn't get it. It sort of bubbled to the top in 2000, maybe 18, when it basically took over everything in natural language processing.
Right. Attention is all you need, and it took off from there.
Yeah. So that's the rest of our course, I guess. We're going to learn about attention. There's also some modifications on RNNs, like bidirectional RNNs, where in addition to using the words that went before a word, you get to use the words that went after it, so that you sort of have twice as much information to work with, and so you can make things a little better using that mechanism, the bidirectional RNN, bidirectional LSTM, and so on. Yeah. Okay, well, thanks again. And Srinivas, as always, I appreciate your insight on this. I know you've taken the Stanford class, so you've seen all this and have a great insight into what's going on. So it's been really helpful to listen to you explain some of this stuff.
Thanks, helped me rethink through these too. So.
Okay, everyone, I'll see you next Saturday then. Have a great week.
Thanks.
Thank you.
Okay, bye-bye.
Thanks, bye.